Well, good evening, everybody. Welcome to CSAR and this slightly warmer February evening. Many of you will know the ropes. We have a great lineup for you this evening. One of our PhD award winners and Simon Warsop talking about your assurance, life assurance and beyond. Well, not beyond, perhaps. The usual rules of engagement, if you'd be so kind. When we come to Q&A, and we'll have one or two questions after Theodor Lundberg's talk, and then an extended Q&A session after Simon's, could we ask you not to use the chat function, please, but either use the Q&A for a written question, in which case I will endeavour to read out questions in order and exactly as you type them. But it means I can do a little bit of shuffling if there's several questions come in which are the same or can be conflated together. Alternatively, if you'd like to be on the telly, by all means raise your hand, and then my colleague Valerie Anderson, who's sitting behind the scenes but has all the buttons to press, will bring you in more or less in turn as we see you asking to speak. So that's the mechanics. Perhaps now I could introduce Theo Lundberg. Theo Lundberg is the PhD fellow in the Department of Physics and has been working on quantum computing. Many of you will be aware that we have an annual awards competition where we invite very promising PhD students to tell us about their work and particularly its application. And Theodor was one of only 10 winners out of 200 applications, so a very select band. Theo, please talk to us if you would.
Thank you very much, and thank you very much for having me this evening. I'll just share my slides now. So in this presentation, I'll be sharing a bit about my research that I've been doing throughout my PhD and also briefly where it's heading. I'm doing my PhD in collaboration with the Hitachi Cambridge Lab here in Cambridge. And my research centers on these devices shown on this slide here, where it's essentially a transistor, which is the key component that you have in your computer and your smartphone. The only modification that we've made to conventional transistors is that we've cut the top part here in half. I'll get back to why it's so important that we use these transistors in our research in a bit. Good. So let's briefly talk about computation. So as I'm sure you are very well aware, computers has driven much of society's advancement in the past decades. And much of that can actually be described what's known as Moore's law, which basically has sort of dictated that that computational power has doubled every roughly 18 months. Now, this trend is still continuing, but slowing down a bit. And if we look at the hard physical limits of how much we can continue scaling computers and computational power, it looks like we'll hit a limit in the next 15, 20 years. But not only that, if we look at economical scaling, which is here we plot the chip size shown here, the computer chip size, and the number here indicates the number of transistors, and then the line here plots the cost, or sorry, the number of transistors that you can buy with $1. So in 2002, you can get 2.6 million transistors for $1, and in 2012, you could get 20 million for $1. But what you see here is that now we're no longer, by scaling, winning economically as well. So it's no longer economically favorable for us to scale, although we do gain computational power still by scaling. So this, combined with the fact that the projected energy demand for computation is projected to increase drastically in the next decade, all these things combined indicate that we should maybe look to alternative routes for computation. And this doesn't mean that we're, of course, at necessarily the limits of computation, but it might mean that we should explore other areas. And one of those is what's called quantum computing, and is what I'm focusing on in my doctoral research. And I just thought I would give you a very brief one-slide picture of what quantum computing is. So essentially, you require some sort of physical system that has two energy levels that are quantized, which means that you can't be between these energy levels. You can only be either in this level or in the upper level. So that could, for example, be an atom can have these quantized energy levels. Typically, very small things have these quantized energy levels. And when you have such a two-level system, it's called, you can create superpositions where you can actually occupy both the lower and the upper state at the same time. And only when you measure do you then figure out which state was occupied. This is also popularized with the Schrödinger cat example, if you've heard of that. And then the other important physical phenomena that you use in quantum computing is what's called entanglement. So entanglement involves when you have two or more of such two-level systems, and they are coupled, so or entangled. Then by measuring one qubit or one two-level system, so this is we call it a qubit as the kind of comparison to bits in computers. But if you have two of these two-level systems and you measure one of them, so say this is your entangled state where the first number indicates the state of qubit 1 and the second number indicates the state of qubit 2. You see that you have a superposition. It's a superposition of these two states. And if you then measure one of them and you get a 0 in that one, you know, because the 0 is stuck together with this 1, you know, just by the virtue of measuring one, you know the state of the other. And this is sometimes called spooky action at a distance, because you simply can know something about something that can be far away just by measuring what is by one of these. And just using these two principles and some clever math and physics, you can do some really, really clever quantum algorithms that have been proven theoretically to be able to allow us to simulate new drugs, do more efficient database search, and solve optimization tasks much faster. So these are all very promising, yet we haven't gotten to the point where it actually is useful yet. What we are currently at is so-called early stage application, where we have 10 to 100 of these qubits, and where we can do prototyping and proof of principle studies. In fact, just about a year and a couple of months ago, Google showed a very nice result where they were able to show for a niche application, random number generation, that actually their quantum computer, which had 54 qubits, was actually better than any supercomputer that we have. So that was the first proof of quantum computers being more useful for a niche task. But in order to access these broader, more transformative applications that were on the previous slides, and really unlock the potential of quantum computers, you need to really get up to a much larger number of qubits. So ideally in the scale of millions. So quite far from the 50 we have now. And notably also you need high quality qubits. So how do we get there? How do we actually build these computers? So there's a number of platforms that allow you to implement this two-level system. So you, for example, have superconducting qubits on the left here. They are currently the most used and most researched. So for example, IBM and Google use these type of qubits. And then there's a slightly younger contender, which is the field that I'm working within, which is so-called spin qubits, where you utilize the spin of, for example, an electron as your qubit. And let me just highlight some of the differences that also point towards why it might be more interesting to consider spin qubits. So first of all, you have the length scale here. You can see the size bar where there's a difference of 3 orders of magnitude with micrometers to nanometers. So you can make these spin qubits much, much smaller, which allows you to build a large scale system easier on less space. And then there's also a parameter called T2, which is essentially your stability of your qubit. So how long you can perform computational operations with your qubit before you lose information. And you have a much higher coherence time for spin qubits. Now, this is the device here that is shown is from an academic lab. So it's not really suitable for being fabricated at scale. And one of the reasons is that you have 6 to 7 electrodes per qubit. And when you scale up the number of qubits, it becomes hard to do the wiring to these electrodes. But since it's in silicon, the question is then, could we actually manufacture these silicon qubits using today's silicon transistor industry? And this is a several billion-dollar industry that fabricates transistors for computers and phones today. So that would, of course, be great if we could leverage that. And that's exactly what we're trying to do in my doctoral work, where we take devices fabricated on very large industry scale silicon wafers, 30 centimeters across, and then we implement in the spin qubits in the corners of these devices. And we've shown that that works fairly well. One thing specifically that we worked on so far is the ability to read the state of the qubit. So whenever you have a computer, you of course want to read information from the system, and quantum states are rather delicate, so you want to be able to read it as fast as possible. And one thing that I worked together with my colleague David Ibbison on was this new design for readout of qubits, and I'm very pleased to share that this is now the fastest way of reading these spin qubits in the world, where we actually managed to do a really drastic reduction in the readout time that's required. So that was quite a neat result. And if we then look at what we'd like to do in the future, we'd like to demonstrate that we can actually also control the qubit. So you can think of that as writing information as opposed to reading information. And then we also want to show that we can easily scale up. So if you imagine on the previous picture, and our work so far has been focused on one of these devices, we have a system where we can go up to 8 qubits here, and you can imagine that you could technically scale this longer as well. So yeah, that's where we hope to go. And at this point, I'd also be very happy to take any questions, and I'd like to thank all the people that have made my doctoral research possible.
Well, thank you very much indeed, Theo. That was smashing. We've got time for 1 or 2 questions. Okay, and I believe perhaps you'd be kind enough to take down your slides, Theo.
Yeah,
and I believe Tony Hooley is coming on screen any minute now.
Hello.
Hello.
Tony, would you like to ask a question?
Yes, sorry, I didn't. I thought I typed it. Do you own the patent, or does Hitachi?
Hitachi owns this patent.
Damn.
Yeah. Well, it was my supervisor who was leading this patent. So, and he works and is under employment with Hitachi. So I think it's quite
fair enough.
Yeah.
Thanks.
No problem.
Great, thank you. Well, I can't see any other questions. You've satisfied all their curiosity, Theo. That was an extremely clear and informative presentation, although I think it's jolly difficult for us to understand the very nano nature of what's going on. It's clearly the way of the future, and delighted to have you as an award winner and talking to us so fluently this evening. Thank you so much.
Thank you very much for having me. Have a great evening, and I look forward to Simon's talk.
Thank you.